Hello friends, welcome to my channel. Let's have a look at problem 2355, maximum number of books you can take. So in this video, we're going to share a solution based on dynamic programming and monotonic stack. So this problem is marked hard in Leetcode. So our plan is to give a detailed, in-depth analysis for this problem. And then we're going to put this solution video to the monotonic stack playlist so that we can compare with other videos on other problems, especially the monotonic call or while loop pattern. So this problem asks us to return the maximum number of books we can collect from the bookshelf. So the condition during the collection is the following. So for each index I in the range, so we must take strictly fewer books from bookshelf I than bookshelf I plus 1. So that's the main statement. So here are three examples. So we're not going to details for this three examples. We're going to analyze some specific examples we cooked up to demonstrate the idea. So the constraints on this problem are the following. First, the number of bookshelves can be up to 10 to the power 5, which is a decent large number. And on each bookshelf, the number of books is greater than or equal to 0. So with that said, I guess we are ready to explain the method. So the method is dynamic programming plus monotonic stack. So actually from the condition here, so this is actually a very strong signal for using monotonic stack. So because we also use dynamic programming, so we are going to first specify what's the meaning of DPI, the generic element. So in this solution, we're going to present. So this means the maximum number of books we could collect from the very beginning up to in bookshelf I, inclusive if we pick all books in bookshelf I. So with this specified, we're going to walk through some examples to build intuition so that we can write this code with these examples in mind. So the first one corresponding to example 1. So here are the things. We're going to look at each index and see from that index to the left how many books we can collect. So at index 0, we can collect 8. At index 1, we can collect 5 here and 4 from the 8. So we get 5 and 4. From index 2, we can collect 2 and we can pick 1 out of this 5. So we have 2, 1. And at index 7, so we can collect this 7 and then 2, 1. That is the result for I equals 2. Similarly, we can pick the books 9 at index 4 and then plus the books we can collect ending at the index corresponding to 7. So that is this number. So the overall result is the maximal of all of the numbers corresponding to the different indices. That is 19 in this case. So let's look at another example. So example 2. So here notice that we have a consecutive increasing sequence. So here for index 0 we can collect 7, and index 1 we can collect 0, and here we can collect 3, here we can collect 4 and 3, and here we can collect 5, 4, 3. So the overall maximal is 12. So with these two examples covered, we're going to look at the third example. The third example actually demonstrates the generic case. So here we have a 0 included, and also we have a consecutive increasing bookshelf books in the bookshelves, and also we have a jump which breaks the consecutive increasing sequence, or if you see from this to the left, breaks the consecutive decrements by 1, right? So in this case, we are going to collect these 3 books and plus the books we can collect ending at index 3. So ending at index 3, we can collect 3, 2, that is 5 books. So the for the books we can collect at index 6 is nothing but the sum of these 3 numbers plus the books we can collect ending at index 3, that is 3 plus 2 is 5. So the total is this number. So example 4 means to emphasize a special number, that is 0. So if it contains 0, actually the zeros break the array into subarrays. So the overall result will be the maximal for each of the subarrays. For example, this 0 breaks this bookshelf to be 2 subarrays, this one and this one. So because all the 2 subarrays are increasing in book numbers, so the return for this one is the sum of these 3 numbers. The return for this one is the sum of these 5 numbers. So the overall return is the sum of the 3 numbers here. So with that said, I guess we get the idea. So typically, if we want to update an index, so it can include 2 parts. One is a consecutive increasing sequence, or if you look at from this to the left, that is a consecutive decrement by 1 sequence. Add this part, and then if we find a job greater than 1, then we can add the number of books we can collect ending at this index. Here the index is 3. So that's the overall principle. So the idea and the specific updating rule is actually completely specified in this part 3. So we're not going to go into details or read through it. So if you have time, or if you have doubt in grasping the ideas, you are welcome to have a look at this part. So before we write the code, let's make a remark. So the stack in the problem will store index and with the check condition below. So the top element in the stack and the number of books. So this is the number of books we want to collect from the stack top index. So that is books I. So if this top index is I minus 1, so we want to collect books I minus 1 books, right? So overall, if it's general index, it will be books I minus this decrement number, that is I minus stack negative 1, the difference in indices. So that is a typical monotonic stack while loop check condition. So you will see. So with that said, we're going to write the code. So we'll split the code into 3 parts. So the first part is an initialization. So we're going to do n equals length of the books. So this retrieves the length information for the number of bookshelves. So then we're going to initialize a DP table, so times m. So this is a routine and also a stack. So I'm going to make a variable called result, and in between, once we set the value for each of the index, we're going to compare that DPI with the result, and we take the maximal of the 2. And finally, we just need to return the result, the state of the result. So with that said, let's look at the second part. The second part is a hyperfunction to update a DP table. So here in place. So for this, I'm going to call this function update. So it accepts this DP table and the left index, so which breaks the decrement. Like here, you can think. So this is I minus 1, I minus 2. So I minus 3. This is the left. So from here, it breaks the decrement by 1 pattern. So this is the left, and then we're going to add from I for each of the index you can think of. So this is the bookshelf we're going to compare or use as a reference. So I'm going to write a annotation. So this is going to collect the books from books I. So with decrement by 1 to the left. To the left plus 1, right? I will see this is the index. And then add collect the books. We can collect ending at index left. That is dp left, right? So with that said, let's do the code. So this is a hyperfunction. So first we are going to check if books I is large or small. So if books I is very large, so when we decrement by 1 up until this left index, we still have books left. So that's one situation. Or the number of books at bookshelf I is very small, and we decrement by 1 to 0 before we arrive at this left index. So that's also a case. So first let's do the first case. If books I is large enough, for example, it's larger than this one, then we're going to compute the number of books from the books I and to this left plus 1, right? So the number of terms is I minus left plus 1. Then we need to plus 1 because this is the one end index, this is another end index, right? So let me directly write this as I minus left. So this is the number of terms. So the two ends. So one end, let's see, is we're adding from books I. Another end is the start. Let's see, is books I minus the difference in index. That is I minus minus left plus 1. So overall, this is books I minus I plus left plus 1. Yeah. So that's the end and start. So this is the total number of terms. And from the start to end, each time the books is incremented by 1. So the total sum is nothing but start plus end times n terms divided by 2. So this is one case. So another case is that we can decrement the books to 0 because the number of books at bookshelf I is relatively small. So in this case, we cannot extend further because we are going to meet 0. So in this book, we are going to collect books is this amount. So in this case, the number of terms is books I, right? From 1 to books I. And the two end, so start is 1 and end is books I. So the S is very easy to compute. Same formula, start plus end times the number of terms, n terms, then divided by 2. So this way, actually, we are ready to set or update the DPI. So basically, DPI, first let's set it as S, and then we're going to collect all the books we can collect at bookshelf I, ending at the bookshelf left. So that is this amount. So we're going to dp I. The increment will be dp left. So if left is a valid index, it's in range. So otherwise, we just at 0. So that's the hyperfunction to update the DP table in place. So next, we're going to look at the third step. That is iterate and get the final result. So this is where we're going to use a monotonic stack. So for this, we're going to use I count enumerate books. First, we mentioned that I equals 0 is very special. If I equals 0, we just enter next iteration, right? So let's first check if a count equals 0, right? If count does not equal 0, what we are going to do is the monotonic stack while loop. So the pattern of this while loop actually is very typical. So you can compare the use patterns in my playlist for other problems. So we're going to check if the stack is not empty, add the stack top element, that is -1. So we are going to check if at this bookshelf we have enough book to pick. Our goal is to pick this number of books, books I minus stack -1, right? So this books I is nothing but count, right? Because we use this enumerative function. So let's see, this is the stack. So this condition guarantees that we can make the check here. So while stack, then we check this condition. Books at the top of the stack is sufficiently large so that we can pick this amount. This is the amount we're going to pick. So this actually corresponding to looking from bookshelf I to the left and each time incremented by 1 when we pick the books. So if this is the case, we're going to do a pop operation. So after we exit this while loop, there are two situations. First, stack is empty, and second, so this condition is validated. So in other words, if this condition is validated, so we're arriving at here, right? Whereas this is continuous by decremented by 1, decremented by 1, then this condition validates. So we arriving at this index. So that's we're going to set the left. So the left is going to be stack -1 if stack is not empty. Otherwise, we're going to set to be -1. In other words, so the decremented by 1 pattern ends at the beginning of the bookshelf. So with that said, we are ready to do the update for DP. So we're going to call update. So we're going to update this DP table, and the left index is left, and the current index is I. So we're going to use this books array as reference. So after we do this update in place, so let's write this update DPI in place. So this corresponding to update the DP table if we view it as a whole loop. So once this is done, we're going to do a standard thing, that is maximum the result at DPI. So with that done, so we're actually almost done. So but don't forget, if count is 0 or in general, so we need to append this I, right? So that's the iteration as a monotonic stack while loop. So with that said, we're going to return the final state of the result. So I guess that's the whole solution for this problem. So in structure, it contains 3 parts. 1 is initialization. 2 is a hyperfunction to update the DP table in place. So you can write this function actually here, but that's a little bit repetition, I would say. And the third step is iterate and get the final result state, and we return. So with that said, let's first do a special case check. Yeah, it passes a special case. Now let's do the generic case check. Let's do it again. It should be fast. Yeah, it passes the generic cases. I guess with this finished, that's all about this this solution format. So you are encouraged to see other problems using DP or especially monotonic stack in the playlist called monotonic stack in my channel. Thank you so much.